All right, buckle up because we are going deep on this one. Picture this. Something that can hold its shape like a rock, but also flow like water without any resistance.
Sounds crazy, right? I mean, that's basically defying the laws of physics as we know them.
Well, it might sound like science fiction, but scientists have actually been theorizing about this bizarre state of matter called a supersolid for decades.
For decades, wow.
Yeah, and now a team of researchers has not only gone and created one, but they've made it out of light, of all things.
Light. Hold on, how do you even begin to make light act like, I don't know, a solid?
Right. It's pretty mind-bending stuff. You sent this incredible research paper over, and it's published in Nature, no less.
Nature, wow.
So we're going to break down exactly how they accomplished this feat and why it's causing such a stir in the physics world.
I am so ready for this. So for our listeners, today's deep dive is all about extracting the key insights from this groundbreaking research by 𝗪𝗏𝗄𝗪𝗪 and his team. We'll also be pulling in some valuable perspectives from articles in Newsweek and Science Alert just to give us the full picture. Absolutely.
We're going to unpack the concept of supersolidity, the mind-boggling method they use to create a supersolid out of light, the evidence that supports their claim, and what this could all mean for the future.
All that and more, right here.
So let's start with the basics. What exactly is a supersolid? I mean, the word itself sounds like a paradox.
Yeah, you're not wrong there. It's a phase of matter, kind of like a solid, a liquid, or a gas, but way more exotic. Imagine a material that has a fixed crystalline structure, just like a solid, where the atoms are arranged in a very specific repeating pattern.
Okay, I can picture that the atoms are all neatly lined up.
Exactly. But here's the catch. It can also flow without any resistance, just like a superfluid.
Like a superfluid, huh? Those are pretty wild too, right?
Definitely. They have zero viscosity, which means they can move forever without slowing down.
So how does a supersolid even work? How can something be rigid and flow freely at the same time?
Yeah, it's pretty counterintuitive. The key is that the particles in a supersolid, while being locked into this rigid, ordered structure, they also share a single quantum state. This weird quantum connection lets them spontaneously organize themselves to find their lowest energy configuration, while simultaneously being able to flow without any friction.
It's almost like they're cheating the system, right? Being a solid and a superfluid at the same time.
Pretty much. Now, this concept isn't entirely new, you know.
Oh, really?
The idea of a supersolid has actually been around for over 50 years, believe it or not.
Wow, over 50 years. But this is the first time they actually made one.
Well, there have been experiments with supersolids in the past, but they were mainly focused on ultra-cold atomic systems.
Ultra-cold atomic systems.
Yeah, basically using these things called Bose-Einstein condensates, or BECs for short.
EECs.
DECs form when you take a gas of atoms and you cool them down to ridiculously low temperatures, almost to absolute zero. And when they get that cold, the atoms start to act like one giant superatom, all sharing the same quantum state.
So these BECs, they were kind of like the proving ground for supersolidity.
Exactly. And scientists have used different techniques to try and create supersolidity in these systems. Things like trapping the atoms in optical cavities, messing around with their spin, or using their dipole interactions.
So what makes this new research so special then?
What sets this research apart is that all previous attempts at making supersolids involved atoms, matter. This new approach is entirely different. They created a supersolid not with atoms, but with light itself.
Light! That's incredible. How is that even possible?
That's the million-dollar question, right?
Yeah.
How do you make light behave like a solid in a superfluid? It all starts with their unique platform. They used a photonic semiconductor made of aluminum gallium arsenide.
Aluminum gallium arsenide. Okay, what's so special about that material?
It's a semiconductor, but unlike the ones we use in our computers, where electrons are the key players, this one's designed to guide and control photons, the particles that make up light.
So it's like a playground for light particles.
You could say that. And on this platform, they created these fascinating things called exciton polaritons.
Exciton polaritons, that's a mouthful.
Yeah, but they're the real stars of the show here. They form when you strongly couple light and matter. In this case, they coupled photons with excitons, which are these bound pairs of electrons in holes that can exist within the semiconductor.
So they created these hybrid light matter particles inside this special material.
Exactly. And they did this within a specially patterned waveguide, which is essentially a tiny channel that confines and directs the light. The waveguide itself was smaller than the wavelength of the light they were using, which is crucial for creating the conditions needed for supersolidity.
I see. So they had their platform, they had their hybrid light matter particles. How did they actually nudge these exciton polaritons into this weird supersolid state?
Well, the research paper highlights the importance of a very specific quantum state called a bound in the continuum state.
A bound in the continuum state.
Yeah, it's kind of a mouthful. They call it a 𝗊𝗋𝗄 state for short.
𝗊𝗋𝗄 state. Okay. What's so special about this 𝗊𝗋𝗄 state?
It's described as a topologically non-trivial state. That essentially means it has certain properties that are very robust and resistant to change. And this 𝗊𝗋𝗄 state is characterized by incredibly low losses, meaning the light trapped inside doesn't easily escape or scatter.
So they found a way to trap the light particles really effectively.
Precisely. The 𝗊𝗋𝗄 state acts like a perfect container for the light, allowing them to observe the delicate supersolid behavior without it being disrupted by any leakage or dissipation. It was crucial for their experiment. And this 𝗊𝗋𝗄 state was formed at a very specific energy level, at what they call the lower branch of an anti-crossing.
The lower branch of an anti-crossing. Okay, I'm trying to follow along here. What's so special about this energy level?
The 𝗊𝗋𝗄 state, at this specific energy level, had two very important properties: a vanishing line width and a negative effective mass.
A vanishing line width and a negative effective mass.
Yeah, no, it sounds kind of bizarre. But those properties played key roles in creating this supersolid. The vanishing line width meant that the light particles were incredibly stable and wouldn't scatter easily.
Okay, so it's like they had these super stable light particles.
Exactly. And the negative effective mass is even more intriguing. It essentially caused the light particles to clump together instead of spreading out.
They clumped together.
Yeah, like they were attracted to each other. And this helped them achieve the high densities needed for the supersolid state. Furthermore, the 𝗊𝗋𝗄 state lacked lower energy states for the particles to fall into, preventing any leakage and ensuring the specific interactions needed for supersolidity. It's like they created this perfect environment where supersolidity could emerge.
Fascinating stuff. So they had their platform, they had their 𝗊𝗋𝗄 state, they had their trapped light particles. What did they do next?
They hit the semiconductor with pulses of laser light. But not just any laser light. It was off-resonant.
Off-resonant. What does that mean?
It means the energy of the laser light wasn't directly tuned to any specific energy levels in the system. It was slightly off, which actually helps to create a sort of reservoir of excited states that can then feed into the exciton polariton system.
Okay, I think I'm starting to get the picture.
So as they increased the intensity of this laser light, the number of photons on the platform started to grow, and they eventually reached a point where they formed a Bose-Einstein condensate.
Ah, a BEC, just like we talked about before.
Precisely. They reached that super low temperature state where all the photons essentially act like a single entity, a superphoton, if you will.
Okay, so they've got their superfluid, the photons are all flowing together without resistance. But where does the solid part come in? How did they create the ordered structure?
This is where it gets really interesting. As they pumped in even more laser light, something called parametric scattering started to happen.
Parametric scattering, all right.
Yeah, it's a process where photons can interact with each other and exchange energy and momentum. In this case, pairs of photons start getting bumped out of that lowest energy state, that central seat in the condensate, if you will.
They were bumped out.
Yeah, into two other states with opposite momenta. But the key is that these new states had the same energy as the original state.
So they're all at the same energy level, but now they're moving in opposite directions.
Right. And this is crucial because it breaks the symmetry of the system.
Breaks the symmetry? How so?
Think of it this way. Imagine a perfectly smooth, flat surface. It looks the same no matter where you are on that surface.
Okay, I can see that.
Now imagine you put a bump on that surface. Suddenly, it's not the same everywhere. You have a distinct feature, a point of difference.
So the bump breaks the symmetry of the flat surface.
Exactly. And that's what's happening here. This parametric scattering process creates bumps in the density of the light particles. It creates a spatial modulation, a repeating pattern in the density, just like the atoms in a crystal.
Oh, I see. So you have the superfluid condensate where the photons are flowing freely, but now you have this repeating pattern, this crystalline structure superimposed on top of it.
You got it. That's the essence of their light-based supersolid.
Wow. Okay, so they think they created a supersolid made of light, but how did they actually prove it? What did they see in their experiments?
Well, they looked for very specific signatures of supersolidity, and they found several compelling pieces of evidence. The first, and perhaps most direct piece of evidence, was that they directly observed this density modulation. They saw this periodic variation in the density of the light particles using a technique called interferometry.
They actually saw the repeating pattern.
Yep. And they measured the amplitude of this modulation, which tells you how strong the density variation is, and it was around 2.6%. That's a significant variation and a clear indication of the broken symmetry we were talking about.
Okay, so they saw the pattern, but is that enough to claim they made a supersolid?
Well, they didn't stop there. They also looked at the phase of the light waves, which is another important property that tells you how the waves are aligned.
Okay, the phase, right.
And they confirmed that the light waves across the entire system were sharing the same macroscopic phase. This is a hallmark of superfluidity and means that all the photons were behaving in a synchronized manner.
So they had the density modulation, indicating the solid-like behavior, and they had this global phase coherence, indicating the superfluid behavior.
Exactly. They also used another technique called Bragg scattering to study how light interacted with their system.
Bragg scattering.
Yeah, it's a way to look at the momentum of the photons. By analyzing the angles at which the light scattered off their sample, they could infer the distribution of photons in different momentum states. And the results they got provided further evidence for the parametric scattering process, the mechanism that created the density modulation in the first place.
So they had all these different pieces of evidence pointing to the same conclusion. They had created a supersolid made of light.
It's pretty convincing stuff. Oh, and there's one more thing which I find particularly fascinating. They found that the wavelength of this density modulation, the spacing between the peaks, wasn't fixed.
It wasn't fixed.
Nope. It actually changed depending on how much laser power they pumped into the system.
That's interesting.
They call this the non-rigidity of the modulation.
Right.
And it's a reminder that this light-based supersolid isn't just a static frozen structure. It has a certain dynamic flexibility, which is a hallmark of supersolidity.
A dynamic supersolid made of light. That's wild.
So what are the implications of all this? Why does it matter that they've created a supersolid out of light?
Well, on a fundamental level, it opens up a whole new avenue for studying this exotic state of matter. Light interacts with its environment in a very different way than atoms do, so this photonic platform could reveal new insights into the nature of supersolidity that we might not be able to see with atomic systems.
It's like a new window into the quantum world. Exactly. And because they can control the properties of their light-based supersolid with incredible precision, they can start to probe the limits of supersolidity and explore its behavior in new ways. This could lead to a deeper understanding of quantum mechanics itself.
That's pretty profound stuff. But beyond the fundamental physics, are there any potential practical applications for this technology?
Absolutely. The fact that they've created a supersolid one light opens up some very intriguing possibilities for future technologies. Imagine being able to create materials that are both incredibly strong and can flow without resistance, all based on light.
Wow, that's a powerful combination.
Right, and they could potentially use this technology to develop novel light-emitting devices, maybe even new types of lasers that operate in ways we can't even imagine yet.
Lasers based on supersolidity, that sounds pretty futuristic.
It does, doesn't it?
Yeah.
And then there are the potential applications in quantum computing. Supersolids could offer new ways to store and manipulate quantum information, which is essential for building powerful quantum computers.
Quantum computing, wow. It seems like the possibilities are almost endless.
It really does feel that way.
Really?
And the researchers are already planning their next steps. They want to investigate the collective excitations within this light-based supersolid, things like phonons, which are quantized vibration.
Phonons, okay.
And they even want to try and increase the dimensionality of their system to see if they can observe even weirder phenomena like rotational symmetry breaking and vortices.
Vortices, those are like tiny whirlpools, right?
Exactly. And they're characteristic of superfluids, so seeing them in a light-based supersolid would be another confirmation of its unique nature.
Yeah.
They're also interested in exploring different mechanisms for creating these light crystals, maybe using different types of light-matter interactions.
So lots of exciting avenues for future research.
Tons. It feels like we're just scratching the surface of what's possible with this technology.
All right, so to recap, we've learned that scientists have achieved a groundbreaking feat. They've created a supersolid out of light. They used a specially designed semiconductor platform, some clever laser techniques, and a healthy dose of quantum mechanics to manipulate photons into a state that exhibits both the rigid ordered structure of a solid and the frictionless flow of a superfluid.
The evidence for this is pretty compelling, and it includes the observation of a periodic density modulation, the confirmation of global phase coherence, and the unique, non-rigid nature of the modulation.
And this isn't just some scientific curiosity. This discovery opens up a whole new realm of possibilities for understanding and manipulating matter and light in ways we never thought possible.
Absolutely. It could lead to groundbreaking advances in photonics, quantum computing, and who knows what else.
Now, for those of you who want to delve even deeper into the nitty-gritty details of this research, we highly encourage you to check out the original paper published in Nature. It's a fascinating read, even if you're not a physicist.
And if you want to explore the broader context, there are some great articles in Newsweek and Science Alert that provide excellent overviews and expert commentary.
So, what other exotic states of matter might we be able to create using similar photonic platforms?
It's a tantalizing question, isn't it?
And how can we control and exploit the unique properties of this light-based supersolid for practical application?
There's so much we still don't know.
The possibilities are truly mind-boggling.
I couldn't agree more.
Well, thank you so much for bringing this incredible research to our attention.
My pleasure.
And to our listeners, thank you for joining us on this deep dive into the fascinating world of light-based supersolidity. Until next time.